In this exercise, we discuss an easy application of the Shannon circuit, whose key idea is to reduce the analysis of an electrical circuit design to that of the truth value of a logical proposition. To understand how it works, let us first recall the two fundamental configurations for component connection in the circuit, namely the series and the parallel. In the series case, two switches, namely A and B, are lying side by side. The current cannot pass if neither of them is on, or if A is on but B is off, or if B is on but A is off. The current can pass only if both A and B are on. On the other hand, in the parallel case, the two switches A and B align parallelly. If both of them are off, then the current cannot pass. Yet, the current can indeed pass if only A is on, or if only B is on, or even better, if both of them are on. Now, the nice thing is that we can identify each of these switches to an atomic proposition. Under this identification, the series can be considered as the logical conjunction, while the parallel can be considered as the logical disjunction. Now, when we look at the whole circuit, by putting all these series and parallel into together, we will achieve a compound statement. Whether the current can pass through the circuit or not is equivalent to whether the underlying compound proposition is true or false. This also indicates that two circuits will be equivalent to each other if and only if their underlying compound statements are logical equivalents. Now in this exercise, we are asked to simplify the following circuit. As mentioned before, by regarding all these switches as atomic propositions, the series as the logical conjunction, and the parallel as the logical disjunction, we can easily write down the underlying compound statement that corresponds to the whole circuit, which reads A and B, or C or A and not B. Let us first apply the distributivity to the second part, which turns out to be C and not B, or A and not B. In this way, the whole compound statement becomes the disjunction of three components. Now, by the associativity of disjunction, we can switch the second and the third term, and then combine the first two terms, that is, A and B, or A and not B. Applying the distributivity for another time results in A and B or not B. But B or not B is a tautology, so that this part becomes simply A. We have finally simplified the original statement into A or C and not B. We see that this time the corresponding circuit is much simpler compared to the original one, which is an interesting application and demonstrates the power of propositional logic.